Hello, folks. Welcome to your lesson on special right triangles. Let's go ahead and take a few minutes to acquaint ourselves with two very good friends of ours. All right, so first things first, your very first special right triangle is what we call our 30, 60, 90 right triangle. And it gets this name because, well, you folks know fully well that any triangle is going to have three angles in it. So we have a 90-degree angle, a 30-degree angle, and a 60-degree angle that makes up our 30, 60, 90 right triangle. There's a special relationship between the sides of this 30, 60, 90 triangle, and I like to give this triangle, because of that relationship, a brand new name. I call this triangle the 1, 2, 3 triangle, and I'll go ahead and tell you why that is. If you look at the triangle, what you're going to see hiding in it, as far as the sides are concerned, are those three numbers, the number 1, the number 2, and the number 3. The 1 is actually hiding in the side that's across from your 30-degree angle because there's an X there. So the short side of this triangle is always what I'll refer to as X, or 1X. The hypotenuse, which is our longest side, is where the number 2 comes from. You can take your short side, this guy right here, and double it to get the hypotenuse. So that's the number 2 hiding in our problem. So we did the 1x, we have 2x, and then this long side here, it's not 3x, it's not triple the size of our hypotenuse. That would be silly. The hypotenuse has to be the biggest side. You'll see that we take our x value and we multiply it by not 3, but rather the square root of 3. So if you want to call it 1, 2, square root of 3 triangle, I guess you have a point. Why the square root of 3? Well, if you think about it, the square root of 3 is a number that is between 1 and 2. If you take the square root of 3 in your calculator, it's like 1.73 when you look at it. 1.73 times the value of x is going to get you a side length that's a little bigger than 1x, but definitely smaller than your hypotenuse, 2x. Furthermore, and if you really wanted a nap, we could take these sides and do a squared plus b squared, and it would indeed give us our hypotenuse squared, or 4x squared in this case. So it's for that reason I call this triangle the 1, 2, 3 triangle, or you could call it the 1, 2, square root of 3 triangle. Any way you slice it, you're going to want to dedicate these special side ratios to memory. On to our next very special right triangle. The next special right triangle we have is our 45, 45, 90 right triangle, also known as our isosceles right triangle. And remember, isosceles from your geometry class just means that two of the sides have the same length in this triangle. So when you look at this triangle, we could also call it the 1, 1, 2 triangle. And I'll go ahead and show you where these numbers are hiding in our expression, or in our triangle here. What I see is one side that's 1x, and because this is an isosceles right triangle, we have yet another side that's a 1x. So what's nice is that if you know one side, you automatically know the other. To get the third side, then you're going to multiply that x value, or the side of any one of your sides, by that factor of the square root of 2. So that's where that number 2 comes from. And this is important because in today's lesson, we're not going to use SOHCAHTOA to find the length of our missing sides, but we're going to use these super special ratios. Let's go ahead and get started. When I take a look at problem number 1, first I identify which of the two special right triangles this triangle identifies with. And when I look at this particular triangle, I notice that I have a 30-degree angle, a 60-degree angle, and a 90-degree angle. So this little gem is going to fit into our very first category of being a 30, 60, 90 triangle, or our 1, 2, 3 triangle. So step 1 is identifying which of our two special right triangles we can categorize our problem as. The next step, or step 2 in this particular algorithm I'm presenting to you today, is to label the sides with the correct ratios. So what we're observing from the diagram is that the side across from our 30-degree angle, all the way over there, is going to be 1x. So I'll locate my 30-degree angle on problem number 1, and I'll go all the way across from it. What they're telling me right here in this problem is that 6 is 1x. The side across from your 60-degree angle, we mark that with x root 3. So this will be x square roots of 3, and then our hypotenuse gets to be 2x. Now, when you do this step, what's going to happen is you're going to end up with an equation that you can really easily solve. So in this problem, I take the value of the unknown and stack it up against the value of the known. So in this case, there's the equation I need to solve to figure out the other two pieces of my puzzle. I'm solving the equation 1x equals 6. In other words, x is 6 in this problem. So that's one side, done. Now I can use this to find the other two sides. Well, if our hypotenuse has an expression associated with it, 2x, and I know that x is 6, I can find the value of my hypotenuse by substituting the value for x into that expression. So if the hypotenuse has a length of 2x, and I know that x is 6, wherever I see an x, I can go ahead and put a 6. Performing this operation, in other words, finding the product of 2 and 6, gives me 12, which is now the length of my hypotenuse. I just have one last side to go ahead and find. This side here, the long side across from the 60-degree angle, is known as x square roots of 3. But once again, I already know what x is. X is 6. So if I just take the value of my x, which is 6, and plug it in, I end up with 6 times the square root of 3, which came from right there. So this side length across from the 60-degree angle is 6 square roots of 3. The last step is to just write the sides from smallest to largest. So my given side was the smallest number, that's 6. The side across from my 60-degree angle would always be your medium length side, so that's going to be 6 square roots of 3. And then your hypotenuse is always your biggest side. That's 12. So the three side lengths there are 6, 6 root 3, and 12. Let's try a 45, 45, 90. So when I look at 45, 45, 90, I think about my 1, 1, 2 ratio. I know that these two sides here have to be isosceles. So if this guy gets to be x, then this guy gets to be x as well. So right now they're telling us, hey, x is 9 in this problem. So if x is 9, then this side over here also has to be 9. The side across from your 90-degree angle, also known as your hypotenuse in a 45, 45, 90 triangle, has the value x square roots of 2. And once again, we know what x is. Make this a different color, make it a little easier to understand. So I know that this is x square roots of 2. Well, we know what x is. X in this problem is 9. So all I have to do to figure out the length of the hypotenuse is take that value of x and plug it in. So this isn't going to be x square roots of 2. This will be 9 square roots of 2. So I now have my three side lengths. Two of them were 9, and then the length of the hypotenuse of the third side is 9 square roots of 2. If you're ever in doubt, feel free to go ahead and check this using our Pythagorean theorem. So if we do a squared plus b squared, you would get c squared. All right, let's dive into one that's a little bit harder. I'm going to go ahead and solve number 6. Number 6, once again, is a 30, 60, 90 triangle. I would go ahead and set up in step 2, after I identify which of the angles or triangles I'm looking at, is to label the sides with the correct ratios. The side across from the 30-degree angle is always your x. The hypotenuse is always 2 of these x's. And then your side across from the 60-degree angle is always x square roots of 3. So what they're giving us this time around in the problem is the idea that x square roots of 3, that side right there, is actually equal to 27. So this is now an equation I need to go ahead and use my algebra skills to solve for. So I'm going to go ahead and take my x square roots of 3 and set it equal to 27. To solve for x, and I notice it's multiplied by the square root of 3. To isolate that value of x, I must then divide both sides by the square root of 3. For you Algebra 3 fans and friends that were really good at Algebra 2, you might recall that we are not allowed to leave a radical in the bottom of a fraction. So it's at this point in time, I do have to multiply the top and bottom of that fraction by the square root of 3. When I multiply fractions, I can multiply straight across. So I'm going to multiply 27 times the square root of 3. And then when I multiply across the bottom, I have the square root of 3 times the square root of 3, which is the square root of 9. I'd go ahead and simplify this ratio if I were you. I have 27 square roots of 3. And then the square root of 9, I know what that is. That's just 3. What I observe in this ratio, once again, is something that simplifies. I have 27 over 3. I can reduce those numbers. 3 goes into 3 one time. 3 goes into 27 9 times. So the value of that side is now 9 square roots of 3. So I now know, because I solved for x, that x is equal to 9 square roots of 3. So that is this side, 9 square roots of 3. To find the value now of 2x, I now need to take just a few minutes to substitute what I know about x in for x in this expression. So instead of writing 2 times x, I now know what x is. X is equal to 9 root 3. So I'll put in 9 root 3 in where that x would go. This is the same as just doing 2 times 9 times the square root of 3, which is 18 square roots of 3. So this expression is now 18 square roots of 3. I put my sides in order from smallest to largest. And to write my final answer, it's going to be 9 square roots of 3 is my shortest side, 27 is the medium side, and then 18 square roots of 3 is our hippopotamus, or our hypotenuse, however you want to look at it. All right, I hope that helps you get a nice jump start on your homework and helps you identify special right triangles.